Yeah, hello everyone to High Performance Computing, Advanced Scientific Computing. The topic of today is really a practical lecture. We have our practical lecture 5.1, Understanding MPI Communicators and Data Structures. It's a jam-packed lecture with lots of examples. In the one area, of course, into communicators, but we also cover a little bit of non-blocking communication. And then in the second part of the lecture, we really think about derived MPI data types, which are, let's say, more simple areas of data structures, and then become to a little example in HDF5, where we use a little bit of binary file formats to show how actually you would work with parallel file systems. It's a complementary lecture to lecture 5, so that's why it makes sense to maybe quickly review a little bit what we have done the last time. So in lecture 5, we started a little bit with looking back when we learned so much about MPI and message exchanges in the first couple of lectures. What is the idea of using it then in parallel algorithms, in parallel applications? And we start with very simple ones where you had just essentially vector addition or matrix vector multiplication, and try to understand what parallel computing really entails to basically have independent parts of computing separated on different processors, and then they do their computing. And at some point in time, there's a message exchange, which is important to gather and collect data together again. And I think the matrix vector multiplication shows it quite nicely that, of course, the way how you do this needs to be a little bit following this so-called domain decomposition that we again revisited last time, because it tells you also a little bit what the application domain logic entails. In our case example here in the matrix vector example, it's really a very trivial math operation where we know the color coding here that we essentially have illustrated here gives you also essentially the domain decomposition and the logic how you would compute and how you would then break this big problem, so to speak, in smaller parallel problems. Of course, you can imagine once you are at the ideas of doing this on the larger scale with oceans that we already have discussed, or you have basically much more bigger domains, that the particles that we also discussed with long range interactions and short range interactions, this becomes not so obvious anymore. So you have seen domain decompositions which are more like tree structures, for instance, to capture the long range interactions and also to work more efficient than with the, let's say, short range and long range interaction in a real application. Another element of the last lecture was also to think about more that MPI can do. And we have seen that more and more parallel algorithms actually don't really always use the blocking communication, so that we have an MPI send and an MPI receive. We have sometimes we call non-blocking communication, where you have essentially an MPI receive, non-blocking, not waiting, right? And this is the interesting difference between the MPI send and receive. These are blocking operations, so essentially they just stop and wait the process to finish, which we have always seen in the ping pong application. Every send has also matching receive. Now this is different with a non-blocking operation, and I will also show some example today in the manner that when you do this, you essentially have something which is not waiting when you have this operation called. It just continues, and you need then certain MPI wait statements. And we come to the situations and the traps of those actually in one of our parallel performance lectures again, where we will reveal a little bit what the complicated issues are when you do this non-blocking communication. Another idea of how to do domain decomposition then in the parallel algorithms we discussed in lecture 5 was that sometimes we have more a really regular grid structure, like the Cartesian grid structure that we said would be, for instance, interesting to propagate a wave over the ocean tiles you see here. And we know in order to do this, maybe in one direction or so, then we need, of course, some knowledge about my neighborhood processors when I want to do the communication exchange. In other words, I need to know who is sending me data. So basically who is having my rank here as a kind of source and destination, where I want to send something to the next tile, but I don't know really what is exactly the rank of this tile. And we have seen that the Cartesian communicator is a very nice idea of giving you exactly this. You know your neighbors. We do a shift and then we obtain the neighbors that we want to do basically communicate with. And we see this example, and we will come back to this example later on, that here the source basically that we get information from is essentially this rank 8 here that actually sends us something. And when we want to send something from our rank 0 here, for instance, we need a destination, and this is then 4. And you see in rank 4, it's the same way. We receive from the source from rank 0 essentially data, and want to forward then in the next time step probably the data then to the next destination. And so in the end, it's a kind of periodic behavior, and you can have this not only in this direction, it's also possible in this direction or even in both, what we will also show a little bit today in part of the practicals. We then carried on in saying domain decomposition is important, but it also captures essential challenges. And this was if you put, for instance, the domain decomposition too little, that you have lots of communication overhead, which is unnecessarily perhaps, and basically the computing will be, you know, idle most of the time because they wait for lots of different message exchanges. So one way also to decrease the number of messages, if you have a domain decomposition, was then a related data structure, which is based on the, let's say, typical normal data types that we would have, like an integer and so on. But here the idea is really to have more complex types once defined, and you can use them then in MPI send receive messages in order to really simplify the message exchanges. And one example would be, for instance, instead of sending just 3 integers here over the let's say in the message exchanges, and then having an MPI send receive for each of those, which would add lots of lines of code. You have just one MPI send receive operation, which is using this new type, which might be 3 times the old type if you would consider an integer. Also, this is more better explained when I do the practicals today. We have seen there are much more interesting, let's say, more elaborate examples when you really want to have larger, let's say, data structures over the wire, which means, for instance, arrays, basically matrices, or a triangle of a matrix that we will also discover today. Toward the end of the lecture, then we covered a little bit in the area of the parallel I/O file formats. And this is a rich topic. We in Jülich, for instance, do 3 days just of parallel I/O and basically workshops around this. So you can imagine this is a really rich topic. I just show some examples also today, how you can work with the hierarchical data format. We pick an example out of the data sciences, which we will also come back to in lecture 10. So the idea is not to really fully understand the clustering today, but much more the data structure, where we have the data of the city Bremen here inside. That is in a sense just a point cloud. And from this point cloud, we want to cluster those points which are close to each other, and then provide some coloring in order to understand and recreate essentially the city that you see. At the same time, we want to indicate noise. Here you see a little bit the kind of small bumps here. There's lots of point clouds around them, which means essentially that was a car with all the laser scans doing, which is of course noise in the city. It's not really the city parts. So let's come to a really jam-packed lecture today by looking a little bit on the outline of the course. Today we will reveal non-blocking communication and blocking communication. Of course, thinking about the weight functions a little bit. But then we really put more emphasis on the Cartesian communicator. We have 2 examples to really understand what is the role of the dimensions, what is the role of the shifts, but also to understand that essentially you need to do the right setup in your job scripts in order to match your communicator dimensions. And I will give you some examples how that could go wrong, of course, when you have not a matching number of cores available for this Cartesian communicator. We will do the application examples on the Jülich cluster, and here is also an early warning. Here, this is basically also part essentially of your assignment number 2, the Cartesian communicator, when you have to implement the ocean, the fishing, and the waves. Then in the second part of the lecture, we come back to the data types period that we had already in lecture 5. So we will quickly review a little bit again why we need the MPI-derived data types, what is the benefit of it. But then we really dive down into some details. I brought you 3 different details, which has also illustrative examples to much more carry away the essence why we need essentially this things like derived contiguous data types or derived vector data types or even derived indexed data types. They all have their benefits. We will look at them and then understand a little bit better why the MPI derived data types are such an interesting area to use. And then we will look a little bit on the idea of HDF5. And this is a little bit a loaded topic because in a sense, we want to have, let's say, point clouds represented in this file. And then we will understand that we cannot even look at this file because it's a binary file format. That makes it really efficient when the processors write, not to, let's say, transform it in some textual, let's say, element that we can really read. It's unnecessary. It's just performance, which is not necessary because the computer works in the binary format. Why we should essentially then drop this to disk then in text file format. So there's a specific tool, however, called HDF5 dump tool, what we can actually use to look inside this binary file formats. And we will look a little bit into it, how we use essentially HDF5 in this very, let's say, rather simple setup of how you can use this parallel IO file formats, also on Newton at the cluster. So let us come to the learning outcomes. Of course, this is really a complex aspect of parallel programming, not only the domain decomposition in terms of the Cartesian, which also includes scheduling the right number of cores, also the HPC environment tools that are available that we have then, let's say, for instance, HDF5, let's say, tool set with the dump, but also with the idea of the data structure behind it with the parallel IO file formats. And when you think about this, this is really a key ingredient in many of the domain-specific applications. So you here have really foundations and approaches of many of the scientific domain applications when you think about HDF5, but also about the Cartesian communicator, and then also about the non-blocking communications. Here and there, of course, the MPI-derived data types are also used. So basically, you have everything you need to work really much more deeper in some of these scientific domain-specific applications that usually always have sophisticated data structures along the way. Let it be the basically plasma physics, where we had all the particles that we basically work with, or basically different domains. You're really able to program and use it then for HPC programming to do different domain-specific applications, mixing it with MPI, but also then application logic. And with this, you can also handle the parallelism very well with these technologies that you have today. It's a broad setup, a very advanced setup on top of MPI, and not really focusing so much on the directly message exchanges here, but rather on the data, on the distribution with the communicators and so on. So starting with the non-blocking communications and the communicator examples. So first of all, we think here about essentially this non-blocking communication. If you remember, we had this already in lecture 4, where we said usually what we did was always an MPI send, has always an MPI matching receive. And basically this is always as it needs to be. But we have also then explored in the last lectures that's not completely true, because here MPI send or MPI receive are a little bit limited. They always are blocking. So once you call them, they will never come back until really the matching send or the matching receive has been essentially then executed. And there's a different way of doing it when we have, for instance, here an MPI I receive, which is then the non-blocking version of the receive operation that just continues to be executing once you have, let's say, initiated it. And that's why we have an MPI wait essentially to synchronize then with any matching MPI send, which is then an MPI operation that you basically have to specify. And I will bring you an example later on. And there are different ways how you can do it. It's not only a non-blocking receive, it's also non-blocking send that you can use. And the way how you handle this with all the different performance impacts here is something we will rather explore in lecture, in our parallel lecture about performance analysis, parallel performance analysis, and much more deep down details of what could be there for problems like late sender and so on. However, this shows you already that non-blocking communication is perhaps not that trivial anymore, like you would know with MPI send and receive. You can also integrate this and of course inside the communicators that you have in the Cartesian grid. No one tells you that you have to do always the same here with all the shifts at the same time happening. So you can also pick some of them. You can introduce non-blocking communication to make really, let's say, interesting real life impacts that then much more are into this idea of modeling. And that's why we call it also in simulation sciences, modeling a domain. You know, basically you would have maybe a very homogeneous way out to do it on the ocean with the wave propagation. But when you then come to the countryside, you maybe have a complete different setup how you want to do this kind of communication. And this could be really then a benefit of this non-blocking communication. This is just here one example how you can use it. So let's review this then again a little bit. What was the benefit of doing this? When we use non-blocking communication, it really usually is enabled to really have computation and communication to overlap. It really can improve your performance, but on the other hand, it can also lead to lots of, let's say, problems in terms of parallel performance patterns, which are really, let's say, can be identified with parallel performance analysis tools, which get you into trouble. And so instead of making improved performance, you actually have less performance. And we will reveal this in lecture 8 a little bit more. We don't put an emphasis here on this just to firstly understand really non-blocking communication before we then go into some examples on this. A couple of other useful methods, the non-blocking send and receive I already said. MPI wait is really waiting for a specific MPI request, which we will see in the example. And then here are some others, like for instance, a get processor name, which really shows you that, or basically on which compute node you're running. That could be interesting, especially for debugging or to see a little bit when you want to have some output where what was somehow computed. We have this W time here, the elapsed time per processor, and there are many others that you have in the MPI implementation, specifications from the standards and so forth, meaning really that MPI is a rich standard. It has lots of operations. Here you see essentially parts of the MPI specification that we're going to reuse in some of the practicals. So let's see and go a little bit to one practical application. And when I do this demo, we have always also the slides that are alongside it. So let's see and look a little bit where we are. You see here, we have the host name, essentially -f. We are on Utune, basically on the cluster, and I told you it would be good to have a directory where you have all your source code in. You see here our history of all the different HPC courses from the past, but here we go into the 2021 one and look a little bit into the MPI codes. Here we have quite a rich setup. Some of them we already had in some of our previous lectures, and we start here a little bit today to really understand now the non-blocking communication. So let's see a little bit what we have in terms of the non-blocking example here. And when we go into this non-block C program that is prepared here already, oops, maybe wrongly written here. Yeah, it's a non-block example.c. Of course, that matters. So here you see essentially now a C program that takes advantage of the non-blocking communication. So what we want to do is we say we have two roles here. We have one which is, let's say, rank 0, that should essentially be representing here the non-blocking sender. And once I do something, here you see we do a little bit of funny text and say, dear task 1, because I'm here, rank 0, please do not send any more messages and so on. With money instead, it's a bit fun. And this is task 0 sending it. So we put this, basically this buffer here that we have, and put it here over the wire. Now, the interesting thing is we have not anymore an MPI send. We have an MPI ISend here, which means really that we add a so-called request here, an MPI request, which is a specific type that we then can use to always wait for, right? We see an MPI wait needs this request somehow to know essentially which one we have to wait for. There are also wait all requests which don't need this, but here we have to have basically a connection directly from this MPI wait that should wait for the specific Iceland to be fulfilled. Although we see directly in this example that the print will directly be executed, right? Showing you that this is a non-blocking operation. It will be executed, we're giving you the output, and then, which makes not completely sense, will then of course wait. In a normal, let's say, program, you would do something with this precious time here and not just wait, or you basically do something and then wait. So directly in MPI wait after Iceland is hardly making sense, right? But of course here as a toy example, it shows you that here the printf is executed, and this could be some computing, for instance. Now you see also that essentially when I'm not rank 0, you see essentially what's happening lower here. When we go a bit down in this, we will have a rank 0 that is sent something to rank 1. So here I need the receive operation now, apparently. So I need to also prepare my buffer. I want to have, let's say, a kind of non-blocking receive. And here's the same way. I need an MPI request to really wait for and to show you and demonstrate you that this is really non-blocking. The idea is really here that we do a printf again. So essentially still we see the hello there user. I've just started this receiving and I'm having good time relaxing. So, and then after this is, fulfilled, essentially, then this request, we can basically come and essentially get the count. So we can use the status of this MPI wait that we have get here, and then get, really the information of how many characters we got and so on from the other processor to really show you that, of course, we really did something. We not only were here in a good time relaxing. So let's see how that materializes when we have the source code. Of course, when you think about the compiling, I will just do this once because by now you know the game. Module load GNU, because it's a dependency to our OpenMPI that we both need as times of the module. We had the compiler MPI CC, which needs a C program, which has MPI directives and MPI functions used. And I recommend usually to make this -o to put a really, let's say, concrete output name, which should be in our case in the non-block example. Every now and then you have some warnings also in your assignment that can happen from time to time. Warnings are not that dramatic, so you can still compile, you have an output and can further work. In this case here, for instance, we can ignore it a little bit. Basically, it's not the most important part of it. What we rather want to show is that it works in parallel and essentially has really non-blocking operations. We need a job script. I think that's clear by now for you as well, being, let's say, finished with assignment 1, essentially. This means that here you have our MPIRun that we learn. We have our load GNU OpenMPI to get the environment and the modules right. So let's see what's happened when we just do this. Batch them. We check, of course, what's happening on the scheduler. We see, it's already completed this non-block example. It has this interesting job ID ending with a 43. So we would expect that there should be some output here somewhere with a 43. And in fact, it's there. So let's look into it, what we will find there. And here we see essentially what's happened when we were executing this. You see, hello there, user, I've done this. And it looks like the message has been sent. And then you have the idea, what we said basically as part of the source code, that this is a different, let's say, processor that is essentially doing this. And then we have the other way around where we say, essentially now we're switching the roles and say, dear task 1, please do not set any messages, send money and says task 0. So we're supposed to rank, right? So this means essentially we would continue with all of this and directly have the output in order to basically do some good calculation normally. And this shows you that this is a really advanced way of using MPI. Okay, so I think this is relatively clear, very simple, but if you integrate it in domain-specific problems, it could be quite cumbersome every now and then. And everything what I essentially said to you is more or less also documented in the slide. You have here the Iceland, the weight, you have the different roles with rank 1, rank 0, and some information about this processor name that I told you. Compute 0 was here, 20 in the example, for instance, to get the processor name, which is quite interesting and can be useful to show, but also maybe here and there to debug. Good, so this is basically then what we did. We did the compilation. I think that was clear. We did the S batch, so it was really then executed on one of the compute node. That's why it's not anymore utun, but called compute 20, as you see here, essentially running really on a compute node. It gives you the output file that we known here in this particular Slurm output. And this is essentially what we've done, running it on 2 processors. Right, coming now a bit more to the Cartesian communicators. So a little bit more elaborate topic. We had them already in a couple of lectures now. We remember MPI Com World is the sum of all the processors. Then we had specific groups. We could actually split groups. We learned that in one of the lectures. But we said also in the last time, in fact, we could do also something called a Cartesian communicator. So when we have a really Cartesian topology as the ocean, that you also will see in assignment 2 is a key ingredient next week when we discuss this assignment. When you want to use it really for a regular communication exchange, you would have periods really where you go, let's say, across the different oceans. You have then dimensions, which are very important and have to match also the number of processors. So let's dive a little bit into the example that we have, right? So this is again the one that we often have seen in theory. Let's see how we put that to practice. We see here we have a 4 times 3 communicator. We have here the rank 0, 1, 2, 3, 4, 5, 6, etc. up to 11. So we basically would require here 12 processors that actually executing then all of these Cartesian grids, would do some computing, maybe the wave calculation on my own tile, for example, and then I send the height of my wave just basically to the next processor. And then this one, while it's doing this shift, should also, of course, shift it then to this. And coming then to the periodic idea of, once I end my ocean here, so to speak, I can start it from the beginning of the ocean if I want. I don't have to do it. There are different ways how to do it, as we will see. So the example that we have here is then essentially creating again our environment that is by now very known to you, MPI Com size, MPI Com rank in the MPI Com world. But we want to create a new communicator. So we create the dimensions here, right? 3 times 4, as we said. Then we said the periodic is something what we want to have. So meaning that here we not only talk about this one, we talk about also the other directions. The reorder basically is also an important thing about should the ranks be getting, kind of new ranks assigned and so forth. So the MPI card create needs then this old communicator, which has all the processes, of course, and will actually say to you, then I require some form of dimension. And in our case, this is the array we defined here, which then includes really this 2D kind of idea how you actually do this. And then we have a kind of communicator, which is really this 2D Cartesian grid here, right? And basically this shows you then when you want to have the coordinates, it really gets the, let's say, the process coordinates in the Cartesian topology, which is of course important to understand when you have some application domain problem. And as I said already in one of the earlier lectures, in the lecture 5, you do a shift in order to understand to, let's say, some direction where you want to go, but this doesn't mean that you really do anything yet. So you didn't communicate it yet. All what you did was essentially understand when you would shift, here basically 1, then you would understand your source and destination. So in other words, to fill this here, the source and destination, 8 and 4, we do a shift in order to understand, okay, when I shift, let's say, to the bottom, I actually need source to get essentially then to be 8, and my destination, the source would be 8 coming from the lower processor here, but my destination when I want to send something down from rank 0 would be 4. I think the best is explained when we go through this now in some real practical example. I also brought you this here step by step. Again, when you think about what would be the dimensions here, the dimension array we have already, the periodics aspect, and so forth. So let's go a little bit again to the example that we have here, Cartesian. For instance, I skipped the compiling a little bit. You can imagine this is the same that we have done. Of course, here we think now about we have a 3x4 grid, so that means we need 12 processes to fill it properly. And I will show you later on an example when we don't have, let's see, this 12, maybe 11 or something, but let's start with 12. Q-start it. So this is running nicely and already actually completed. So we're looking for a job ID output for a 44 at the end. And we do SMSL. We maybe here and there have to wait a little bit. There it comes. And then when we do the more and a look into this, we basically see the following output that essentially reproduces a little bit what we have seen here. So, you know, basically it gives you all this printing outs. We could look a little bit into this source code to understand it. Here's a clear. Oops, up. There. A little bit hanging here. So let's look a little bit into the card example to understand what's happening. Essentially, here is the same I already presented to you. We clarify the dimensions, we say the periodics, and essentially then creating here down there the Cartesian communicator exactly with this information, the dimensions, the periods, should we reorder them, and then basically have a new communicator called 2D, which is now the 3x4 grid that we discuss. I can obtain then here, and remember that this is now 12 times executed. Right, the same source code. And as I don't make a rank change or an if statement about the rank, you can imagine, okay, that's essentially what we keep here in terms of every rank is going through this. So in other words, every rank is then part of this Cartesian communicator. And with this also is created basically or getting this different, let's say, coordinates inside this Cartesian grid. Right, and we want to, of course, now think about what we do when we here receive something to the different, let's say, neighbors, so that you see always a debug output here. So from the rank that I have and the source and the rank into the destination, similar likely we basically have here, right? The rank and the source and the destination. And this gives us then the idea how we essentially then can really obtain the output here when we run it. Or basically not when we run it, but when we look into the output here. Again, it's exactly revealing this. When we take one, we have essentially, again, our rank 8. This is maybe an example here where you say here, this is rank 8. We say the destination should be 0. Why is that? Because we had periodic true. So essentially it sends something to destination 0, which is our rank 0 here. And essentially we send the other way around. We need something that is coming to us, saying then essentially what is our source, which is basically then the 4 for my 8. Interestingly enough, you see also what's happening in the Cartesian grid. What's interesting for in the Cartesian world, the coordinates, to understand it, this was now 2, 0, right? Which is now saying it's essentially the second row here, not the 0 row, not the first row, the second row, right? Starting always with 0 here. So the Cartesian grid coordinates, you have a 2, 0, which could be quite handy to know. Right, so this was, let's say, a very easy example of the Cartesian communicator. Let's see a little bit how that works when we now think a little bit towards your assignment. So when we want to have, let's say, a communication exchange, which is a bit more interesting, we have essentially the same setup again on the slides that I just showed you as a Cartesian create. Here's again the periodic idea that you don't necessarily only have to do it this way or that way. You can also have it basically in this way, or even as we just did, combining both, right? And of course, the matter how you shift will influence this, which is an important part in it. So we have this coordinates from the Cartesian grid. You have seen 2, 0. It's completely different from the rank, essentially. So it's now a different world. It's Cartesian coordinates. And we have seen that we basically do a shift in order to obtain the source and destination, but we don't really do something. We don't send and receive yet, but we use, of course, this information to send. Now, when you think about the standard shifts that you would do is a positive shift and a negative shift to one direction or the other, I think that is relatively straightforward to know. What's, of course, a bit tricky is what happens when you don't have a periodic shift. Let's say problematic shifts in negative shifts in periodic are, of course, fine, because then you will go back to the, let's say, processor that is just basically come around the periodic once again. But when you have the non-periodic way, you will end at the ocean, so to speak. You fall into the non-ocean or something like this, right? There must be some specific element called MPI proc null that you can always use as a kind of dummy process that say that the next shift is essentially going out of the dimension of the Cartesian grid if you have really a non-periodic setup. So then we said send receive is quite still important. So it's really doing something and using then, of course, the source and destination. The interesting thing is now really to understand that this is executed 12 times on different processes, right? So all source and destinations that are filled here by this Cartesian shift are, of course, different, right? Because everybody sits on a different Cartesian coordinate. And that's, I think, important to understand also for your assignment. Think about when you are in the Cartesian communicator example, that your world that you have there is shared, that basically the program executed is several times executed, but luckily every process in this world of the Cartesian world will get its own Cartesian coordinate depending on the rank. So, and I think this is relatively straightforward, as I did here with the card example. Then I just wanted to demonstrate you another interesting example that you see over here. When we have seen that this output was quite okay. The trouble is when we do now for the following and say, sorry, I'm just in the wrong one here. Still in the Cartesian maybe. Here and do submit card example and would take here just 11 cores maybe or processors. Then you can imagine we have a 12 grid, a 3 times 4 grid, which means 12. And when we dispatch this now, and we have just 11 from the scheduler, we have somehow a clash, right? So we have just essentially 11 ranks. We have 0 to 10. We don't have a rank 11. So essentially, when you look at this a little bit, what we have here, this fellow is missing here, the bottom right. And this gives us, of course, a trouble when we want to work with this. So what we expect is that this is not going to work. So we would have probably something that we see here in the 45, which is probably very soon finished here. We see already there's some trouble here. If you look into the output, it's not as much output as the others. And we see it's actually not really fitting to the processors that we have there. It makes a fatal error and you cannot work with a Cartesian. Right, but let's see what would be one example, which is a little bit more elaborate from this, what you have already seen here in the example, which is going also towards your assignment, also using and combining this now with non-blocking communication and the Cartesian communicator, where we have, let's say, a 4x4 grid, not anymore 3x4. But of course, the idea how to do it is very similar. You have the dimensions here that you can specify 4 times 4. The reorder, everything remains the same. Now we want to basically send and receive quite something. We want to have, basically define here essentially up, down, left, and right, which is for convenience, for code readability, to really send things, let's say, to this different areas, left and right. And it's also something that might be interesting for your assignment to pick up. And then in the MPI init, we do the same thing we just have done. I think this is all creating very similar this Cartesian communicator that you have already seen. But now, of course, with the dimension 16 by 16, we have the Cartesian coordinates that we can then obtain. And here you see now in the neighbors that I define, essentially from my all neighbors surrounding me, in the basically setup that we have. Of course, when you think about one grid item, I have 4 neighbors here, and I can say I pick one of them, right? I have a neighbor up, down, left, and right. And when I want to do something with them, you remember before I send something, really, I need to shift first to understand what are my neighbors. So what are my neighbors up and down when I shift, let's say in this one region, when I shift in the left and right, let's say region. So this is how I fill essentially now my neighbors without communicating yet. I still use the MPI environment to get to know what are really the ranks I'm talking about. And then you basically can do and print out that this information is filled. And of course, then we should do something with this information, and we put to basically do 4 times message exchanges. Now think about that this will be 16 times executed. So every processor is doing this exercise, right? And this is, of course, quite an important part in it, to essentially thinking about that this is many times executed. We have here non-blocking send and essentially a non-blocking receive. I do this 4 times in the loop, but I also receive 4 times, of course, from my neighbors. And here the 4 can be cancelled as an offset in a sense. But you see, in the end, we have, let's say, 8 requests we're waiting for, right? Because we sent something to all the neighbors and receive something from 4 neighbors. So which means really you have to wait then for all this 8 requests here in this wait all. And my suggestion then, it's a little bit a simplified code. So my suggestion for your assignment is to really reuse this part. And we will talk about it next time. Basically, when we see then how that is basically alluding then to the ocean that you should do. So let's go a little bit to the practice again and use this Cart2D, which you basically can use as a base for your assignment in order to create the ocean. So we have the Cart2D.c that you see here with the write down essentially what we already do, and have here all the for loop, which is performing the non-blocking communication you see here, essentially, and then waits for all the 8 requests to finish. Of course, normally you would do something, compute the waves, compute something, which is, you know, the idea then of using parallel computing. Here it's just purely the message exchanges, which is, of course, more or less here a simplified demo code. However, the good thing is it gives us an idea how it works. In terms of the Cartesian grid, we remember we don't have 12 anymore. We need 16 now because we have a 4 times 4 setup. But everything else essentially is very much the same. You do an S-batch, you submit, and then basically wait until that's finished. The 2D example. After some time, so we're looking for an output which is the 46. And we see here's an output with the 46. And when we look inside this, what we expect is now that we know the neighbors, right, that are obtained by the switch. But also when I then basically have really sent something, that I have received also essentially then the ranks of these communicator neighbors in the Cartesian grid, which makes it now interesting because we essentially never defined really the neighbors. It was coming all from the Cartesian communicator automatically. And this is, of course, the power that I wanted to demonstrate in this communicator. Think about that you have a much higher grid, which is quite interesting. So all what I just did essentially is already here on the slide. So I think that's all what I wanted to leave you on the table for the first part of the lecture. And we break here for a short period and then come back to the second part of the lecture.